Hello everybody, welcome to the Ultimate Physics channel. In this video, I am going to solve some problems on classical relativity, which includes topics such as the inertial frames of reference and the Galilean transformation equations. The first problem here is show that Newton's second law has the same form under Galilean transformation. That means we have to prove that the Newton's laws are invariant under Galilean transformation. That is what we have to prove. Or invariant under Galilean transformation. Right? So how do we set about to prove that? We know that the second law of Newton's force is equal to mass times acceleration. We have to prove that this expression is invariant under Galilean transformation equations. So let us consider two frames of reference which are both inertial. So let us consider two inertial frames of reference. K, let's say at K prime. That means you have a frame of reference K, and you have another frame of reference under consideration which we call K prime here. And let us say that this particular frame K prime is moving with a relative velocity, let's say at v, is moving with a relative velocity v with respect to K. Now how will we write the Galilean transformation equations for this? The Galilean transformation equations for the same, that is for this particular situation, is Galilean transformation equations are basically, in this case, for the K prime we have x prime coordinate, that is going to be x minus vt, because the positive, along the positive x direction, there is this relative velocity v. So the two frames are relatively moving along the positive x direction. So we have x prime is equal to x minus vt, y prime must be therefore is equal to y only, z prime is equal to z. Of course, according to the Galilean transformation equations, the time is anyway invariant across all inertial frames of reference. Right. So if this is the situation, then we can write by deriving the what is called the expression for the velocity transformations using the Galilean transformation equations by taking derivatives of this x prime, y prime and z prime. So let us say ux prime is equal to dx prime over dt. So we have x prime is equal to x minus vt. Therefore, our ux prime would be equal to ux minus v, where ux is nothing but dx over dt. So this is our expression. And similarly, if you take for the other coordinates, this y prime, we would naturally get uy only here, and for the next coordinate z prime, you will have uz, right? Now if we take the second derivative of the displacement, that is x prime, as ax prime, which is acceleration. So these three are velocity derivatives. Then for the next term we get acceleration, that is derivative of velocities, that is ax prime is ax time derivative of this particular expression. Then of course ay prime is acceleration uh, in the k prime, the same coordinate along the y direction, which is equal to ay, and az prime is equal to az. So we have gotten these three equations now. We know that F is equal to mass times acceleration, so force is equal to mass times acceleration, means we have Fx prime is equal to m a x prime, Fy prime is equal to m a y prime, z prime is equal to m a z prime. Therefore, we are getting the expressions in the k prime coordinate for force as generally F is equal to ma, which is the same as the expression that we would have in other frame of reference, let's say k. So the Newton's second law is the same in both k and k prime. So any other inertial frame of reference is equivalent to k prime. Therefore, the Newton's second law holds true in all inertial frames of reference, and it has the same form which was originally asked in the question. So it has the same form in all inertial frames of reference, right? So hence proved. Right, next we move on to the second problem. Show that the expression for linear momentum p is equal to mu has the same form under Galilean transformation. So here specifically the expression has been given as, momentum expression is given as p is equal to mu. So simply, just like how we proved for force, we have to try to prove that. So let us take here also two frames of reference. Let us say now S and S prime, be two inertial frames. Again they are let us say under separation by constant velocity. Let us call inertial frames, two inertial frames with relative velocity let us say in this case is v, right? So we have the first frame of reference, which is having origin O here, and let us call it S, and the next frame of reference, let's call that S prime, whose origin is, let's call that O prime. This is moving with the velocity v with respect to the first frame of reference. Here the coordinates are x prime, y prime and z prime, whereas here it is x, y and z. Now the momentum of any object in this particular frame of reference, that is S frame of reference, is given by p is equal to mu, where u is the velocity of that particular object in that particular frame of reference S. Now you can define therefore u as derivative of the displacement x, so it is dx over dt. Now Galilean transformation equations, we know that, or x prime is equal to x minus ut, which will transform a set of displacement equations for displacement in these two frames. So it is y prime is equal to y, z prime is equal to z. These are the expressions. Now in the S prime frame of reference, what we have here is the momentum expression p prime is equal to m, let's say u prime, going by this, assuming that these two are going to be invariant. So under that scenario, we will have this as equal to m into dx prime over dt, right? That d and d prime are same, so we can just leave it as d, and therefore I can write P prime, which is the momentum in the S prime frame of reference, as d over dt of x minus vt, right? That will be m into the first term derivative is dx dt minus the second term is just v, and this would be mass times velocity u as per our original definition, and then this is v, or we can say m into u minus v, which is a velocity difference in velocity. Therefore, this is somewhat, I mean, not somewhat, this is equal to, equivalent to p is equal to mu in the s prime. So this is s and this is in the s prime coordinates, right? So that's why we can conclude that the expression for linear momentum, whether it is p is equal to mu or mv, is the same across all inertial frames of reference according to Galilean transformation equation. Right, let's move on to the next problem. Right. This problem tells us that an infinitely long wire carrying uniform charge lambda per unit length is fixed to an inertial frame S. So let's try to just draw a diagram for this. We have an an infinitely long wire. So let me draw a long wire, right? And it is carrying a uniform charge lambda per unit length. It is fixed to an inertial frame, let's say an inertial frame S here. Another inertial frame S prime, which is moving with the velocity v, right, with respect to S. Now observers in S and S prime, let us call these observers as O and O prime. These observers measure identical electric fields equal to 2k lambda over y1. So the electric field here, let us write it down, 2k lambda over y1 at a distance y1 is equal to y1 prime from their respective origins. So you have a situation where an electric field is measured at a point, a distance y1 from the origin of this coordinate. Similarly, for the other coordinate, it is y1 prime. From the origin, if you measure the electric field due to this wire, that is going to be y1 prime. And here it is given as these two are being equal, the distances from their respective origins, O and O prime. However, the observer in S prime, that is this one, measures an additional force on a test charge Q equivalent to this expression. So there is an additional force component here for the observer in this particular frame of reference, that is minus mu naught lambda v squared Q over 2 pi y1 or y1 prime, or like this, because these are equal anyway. So this is the additional force that he measures due to a magnetic field at y1 prime arising from the motion of the wire in the minus x prime direction. Minus x prime because this is moving, s prime is moving to the right. So with respect to s prime, s is moving towards the left with a velocity minus v. Therefore, it is minus x direction for s prime. So it is minus x prime direction for the observer in s prime frame of reference. Now the question is, what would the relative velocity of the inertial frames need to be in order for the S prime observer to measure no net electromagnetic force on the test charge Q? So the question here is, in one frame of reference there is only electric field. In the other frame of reference there is an electric field plus a magnetic field. due to the motion of the conductor, because the conductor uh, is moving with respect to s prime, that is, it is at rest in s frame of reference. Since it is moving in s prime frame of reference, the conductor must produce also a magnetic field. And because of this magnetic field, there has got to be a magnetic force, which is given by this expression, which is minus mu naught lambda v squared q over 2 pi y1, where mu naught is of course absolute permeability or permeability of free space. Lambda is the given charge per unit length or linear charge density. V is the velocity with which S prime is moving with respect to S frame of reference. Q is the test charge that is used to measure this electric field. And distance y1 is from the origin to the particular point where the test charge is kept and the electric field is measured, where additionally now because of the apparent motion of S with respect to S prime, a magnetic field is also generated and therefore a magnetic force is felt by the test charge. The question is, what should be the velocity v if the electromagnetic force on the test charge is cancelled? There is no net electromagnetic force is felt by this particular charge. That is the question here. So let's try to solve this one up. Right. Now this thing is, we know the force expression in electromagnetic theory, that is the Lorentz force, right? That is only the electrical part of that is Q times the electric field. Of course, the entire expression for the Lorentz force is a charge Q times E plus V cross B. This is the expression for Lorentz force, the electromagnetic force on a test charge in an electromagnetic field. Now, in this particular case, the electric part alone is the first term of this expression, and in the S frame of reference, so I write S frame of reference. Let's say frame S. The force Fs is equal to 2k lambda by y1 is the given electric field. So the electric field is 2k, and the question this is given as lambda over y1. Since we want to write force, using this expression we can say it's 2k q lambda over y1. This is the expression for the force. This is net force in S frame of reference. Now in frame S prime, the net force is, let me call that Fs prime, that would be equal to, same force is measured, so 2k lambda over y1, 2k q lambda over y1, minus the additional term is here given as mu naught lambda v squared q over 2 pi y1, right? Now the question it is asked is, what is the velocity for no net electromagnetic force? So no net electromagnetic force would have this Fs prime to be equal to 0. No net electromagnetic force in S prime. That is the condition. For that, this has to be equated to 0, right? That means we have this term, whatever we have written here for Fs prime, that would imply 2k q lambda over y1 minus mu naught lambda v squared q 2 pi y1 going to 0, right? Or these two terms can be equated directly. right? That case we can see that what are the terms that cancel. Here lambda will cancel, q will cancel, and y1 will cancel, right? So we have 2k is equal to mu naught v squared over 2 pi. Or we want velocity expression, right? So v squared is equal to 4 pi, if I take this to the side, 4 pi k mu naught, sorry, over mu naught, right? Mu naught will be in the denominator here. So v squared is equal to 4 pi k over mu naught, where k is my in electromagnetic theory, we know that k is 1 by 4 pi epsilon naught in the SI unit system. So it is v squared is equal to 4 pi into 1 by 4 pi epsilon naught, 4 pi over mu naught, right? So we have here 4 pi cancelling each other. So v squared, sorry, so v squared in this case is 1 by mu naught epsilon naught, where epsilon naught is the permittivity of free space and mu naught is the permeability of free space. So v, if you write, you have 1 over square root of mu naught epsilon naught, which we know is expression for the speed of light in electromagnetic theory. So this is equal to c. Therefore the condition, if v is equal to c, that is the velocity with which the s prime frame moves with respect to relative to s frame, is if it is equal to the speed of light, then no net force. That is the answer to the question. So the net force felt by an observer in s prime frame of reference is nullified provided he moves with the speed of light, right? Okay, so let's move to the next one. Right. Next question is, a probe is launched from the spaceship of an advanced civilization of an exoplanet towards Earth at a speed of 2.1 into 10 power 8 meters per second. So a spaceship, let's say, is trying to kind of send a probe, right? Right. Is trying to send a probe on nearing Earth, let's say. They're trying to send a probe. And the spaceship probe speed is, let's say, some kind of a probe is being sent. The speed of the probe is 2.1 into 10 power 8 meters per second, right? The velocity with which such a probe is sent. Let's call that as v. The spaceship itself travels at a speed of 2.3 into 10 power 8 meters per second. Okay. Now using Galilean relativity, what would be the relative velocity of the probe with respect to the Earth? Can the probe be seen before it lands on the Earth? That is the question, right? Right. Now velocity of the probe with respect to Earth, if this is the Earth, what is the velocity of the probe with respect to the Earth? Now according to the Galilean transformation equation for velocity, we know that it is in the s prime frame of reference, let's say ux prime, that is going to be equal to ux minus v, right? Here we are fixing the frame of reference, okay? right? In this case, we can say that the S prime frame of reference is fixed to the probe, rather the spaceship. So in this case, we can say that S prime frame of reference is fixed to the spaceship and the S frame of reference is fixed to the Earth. Then we need the velocity of the probe with respect to the Earth. So ux is equal to ux prime plus v. So ux is going to be equal to just a sum of these two velocities, because this is the velocity of the probe with respect to the spaceship, which is ux prime case. Therefore, ux is equal to a sum of these two will be 4.4 into 10 power 8 meters per second. This is the speed, and this ux turns out to be, if you apply the Galilean expressions, greater than the velocity of light, which is 3 into 10 power 8 meters per second. Now, since it is greater than the speed of light, we can say that can the probe be seen before it lands on Earth? No, because the speed of the probe is even greater than the speed of light. So the speed of the probe with respect to Earth is, since it is greater than the speed of light, we can conclude that it is not possible for observers on the Earth to see the probe before it lands, right? Okay, so let's move to the next question. Right. Yeah. Two cars travel at constant speed in the same direction with velocities 120 km per hour and 80 km per hour with respect to ground. What is their relative velocity? Now, it's a very simple problem. We can use the Galilean arithmetic equations to arrive at these relative velocity. Let's say car 1 has a velocity. First car we call that as car 1. It has a velocity with respect to ground. So we say with respect to ground, right? With respect to ground, the velocity is, let us call that as Vx prime. That will be given as 120, right? So it's 120 kilometers per hour. Vx, let's say. Now car 2 is another frame of reference. So with respect to ground, again, its velocity is Vx prime, let's say. That is equal to 80 kilometers per, 80 kilometers per hour. That's what is given here, right? Now what is the relative velocity? So if you use that equation, Vx prime is equal to Vx minus u. You want u here, so u is equal to Vx minus Vx prime. And that would be 120 kilometers minus 80 kilometers per hour. So the relative velocity between the two cars is 40 kilometers per hour. That is the answer to this question. So we are fixing the, let us say in this case, in this equation, the S prime frame of reference is fixed to the ground, right? Because with respect to ground we are writing. And S is fixed to the ground, right? Because here Vx, so it is fixed to the ground, and S prime is fixed to the car 2. Only under that condition we can write this expression, and then we can get the relative velocity as u. Right. Let's move on to the next problem. Right. This question is Yeah. So sixth problem. An aeroplane is flying due west at a speed of 360 kilometers per hour with respect to still air. If a wind of 60 kilometers per hour blows towards south with respect to the ground observer, what is the velocity of the aeroplane with respect to the ground observer? What is its direction? So what is given here is we have to these are the directions. So let's mark this as north south, and then we have east west, right? So an airplane is moving due west. Where is the side? Let's say at 360 kilometers per hour with respect to still air. But if the wind is blowing towards south, there is a wind velocity that is cutting across this, right? And if it is moving at the wind velocity is at about 60 kilometers per hour towards south with respect to the ground observer on Earth, right? What is the velocity of the airplane with respect to the ground observer? What is its direction? Airplane's direction. What is its direction? So we can say that we can fix the frame of reference S to the ground, right? So let us fix the frame of reference as respect to the ground. Yes. So let S be fixed to the ground. Right? And S prime be fixed to the wind, because wind is blowing at 60 kilometers per hour. If that is the case, here in this diagram, we can say that wind is blowing towards west, right? So we can have frame of reference fixed to the wind. Here let us call that as the x prime direction. So our x prime is along the north and minus x prime is along the south, and then y minus y prime is along the east, then and then along the west you will have y prime, right? If we take like this, then we can say that the velocity of the airplane with respect to wind, if you write here the relative velocity, the velocity in this expression we have of wind is 60 kilometers per hour, right? So we can say that in our expression, Galilean transformation expressions, u is equal to 60 kilometers per hour, right? And therefore Vx prime is equal to 0, because S prime is fixed to the wind, right? So it is 0, and Vy prime is equal to minus 360 kilometers per hour, right? Right. Then we can say that we can use Galilean transformation equations and right, try to solve this one. Vx is equal to Vx prime plus u, which is equal to 0 minus 60, because wind blows along the south direction. So in this case, relative velocity has a minus sign because north is taken as x prime in our selection of coordinate system. Therefore, this is minus 60. So I write directly Vx is equal to minus 60 kilometers per hour. Because of that reason. Now, what about the y component of this velocity Vy? That would be equal to Vy prime, because there is no movement in that direction. So Vy prime is therefore equal to 360 kilometers per hour. And here also minus sign because our y is to the right x, but wind is going to the left, so here also there has to be a minus sign. We have to take it there. Now relative to the ground, the aeroplane flies in a direction determined by an angle theta, which would be tan inverse of these two vectors, right? That is minus 60 is one, and then the other one is minus 360 degrees. That would be tan inverse 1 by 6. Right, that is, I think theta is around 9.5 degrees. And what is the direction? The directions are north, and this is east, right? And because wind is blowing this way and airplane wants to fly this way, wind is blowing down, airplane wants to fly this way, wind is blowing down. So this is going to be 9.5 degrees to the south of west, right? That is 9.5 degrees. So 9 degrees south of west. That is the direction in which the airplane has to be moving. Okay, right. That was the problem. So the seventh problem. A woman is piloting a small airplane in which she wants to reach a destination that is 750 kilometers due north of her starting location. So she wants to go 750 kilometers due north. Let's mark this like this. Hmm. Okay. So a woman is piloting a small airplane in which she wants to reach a destination that is 750 kilometers due north of her starting location. So we have north direction, let's say along this one. So she wants to reach some destination, let us say at 750 kilometers from a starting point here. Once she is airborne, she finds that due to strong but steady wind, to maintain a northerly course, she must point the nose of the airplane at an angle that is 22 degrees west of true north. So this is 22 degrees. Her plane has to be pointed in this direction so that the wind takes her to true north, her desired destination. So from previous flights on this route in the absence of wind, she knows that it takes about 3.14 hours to make the journey. With wind blowing now, she finds that it takes longer time, that is 4.32 hours. A fellow pilot calls to ask her about the wind velocity, that is both magnitude and direction. What would be her report? That is about wind and other direction, right? So we can say that without wind, um, the speed, right? The speed is equal to 750 kilometers, taking 3.14 hours. That was the velocity, right? That is 238.9, let's say, kilometer per hour. Now with wind, this is going to be 750 speed, right? over 4.32 hours. That is going to be 173.6 kilometers per hour. Now here if you can see that these are the two vectors, right? The one is the actual direction, desired direction, the other one is the direction taken. So wind has to be blowing as a vector sum of these two vectors. Therefore we can straight away say that if I keep these two vectors, this direction, these two vectors, so I know that the wind is going to blow something like this. So the wind direction is just a vector addition of these two vectors, and that is this direction, right? That is like southwest direction is the actual direction in which the wind might be blowing. Therefore, now we have to see that there's two components to this wind velocity. There is one along the southern direction, the other one is along this direction, that is the eastern direction. So we can take the two components and calculate them separately in this case, right? So we can say that wind velocity along the southern direction is given by 238.9, that is the actual speed in the absence of wind, and there is a 22-degree shift here because of the speed of the wind, so that is cos 22 here, the cos component of this thing here. So we are taking a cos component with respect to this particular direction downwards, so it is 238 point cos 2. Now the difference is with wind here we have a speed that is reduced, that is 173.6. So if we do the calculation for this one, we would get about 47.9 kilometers per hour. Similarly, wind velocity along the eastern direction, wind velocity along the eastern direction. The flight there has no component in that direction, so along this direction it is easily 238.9 sine 22, and that is equal to 89.5 kilometers per hour. So these are the two components of the velocity. So resultant wind velocity is equal to square root of square of this and square of that. So v square, let me call that, and v y square. That would be the calculation. It is about 101.5 kilometers per hour. This is the speed with which wind is blowing, and the direction of wind speed is theta. Let's call that is theta of tan inverse of these two components, that is 89.5 is first thing, then 47.9 is other one, right? So 47.9, that would be 62 degrees, and since it is blowing like this, it is 62 degrees south of east. This is east, this is south, so this is 62 degrees south of east. So the report to the other pilot, fellow pilot, would be that the wind is blowing at about 101 kilometer per hour, and direction is about 62 degrees south of east. That would be her report. Right. The next question: a moving sidewalk, 100 meter in length. Let's call that sidewalk as sidewalk. It carries passengers at a speed of 0.5 meters per second. So the motion of this is about 0.5 meters per second speed. One passenger has a normal walking speed of 1.25 meters per second. First A, if the passenger stands on the sidewalk and without walking, how long does it take for her to travel the length of the sidewalk, the entire length, if she starts from one end to reach the other end of the sidewalk without walking? That is, this is 0. What would be her this thing? So A part is there. The answer is going to be the speed of the sidewalk. So for the first part, she is not walking. So let me write no walk. She is just standing on the sidewalk. So the speed has got to be 0.5 meters per second. So what is the question here? If the passenger stands on the sidewalk without walking, how long does it take for her to travel the length of the sidewalk? So the time is going to be the distance, 100 meters, over the velocity, that is the velocity of the sidewalk. So that is going to be 200. This is meters per second, so answer is in seconds. Right. The next one, B. If she walks at her normal walking speed on the sidewalk, that is at about 1.25 meters per second, then what would be her time? How long does it take for her to travel the full length? Now walk at 1.25 meters per second. Now the time is the same distance, it is so 100 over the speed is now along this direction in which sidewalk is moving, so it is going to add, right? So the speed is going to be 1.25 is her speed plus the speed of the sidewalk, that is 0.5. So it is 100 over 1.75, and that will be equal to 57 seconds. Right, it's roughly 57 seconds it is going to be. And what is the third part? The third part is C, right? When she reaches the end of the sidewalk, she suddenly realizes that she left a package at the opposite end. She walks rapidly back along the sidewalk at double her normal walking speed to retrieve the package. How long does it take to reach the package? So now she forgot something on the starting point, so she comes back to take it and she walks back at twice the speed in return. So now what is the time? So now return at the double speed, double the speed, so to say. So that is t is equal to, the distance is again the same 100, but now she walks at 2.5 because earlier it was her velocity was 1.25. Now she is doubling her speed, that is about 2.5 meters per second, and of course plus the sidewalk is moving, but here you can see that in this case, if the sidewalk is moving towards the right at 0.5 meters per second, she initially starts from here, goes here at 1.25, then realizes that a package was left here, so she comes back in the opposite direction, so the speed has to be subtracted from here, and that would be 100 by 2. That is going to take her 50 seconds at double the speed as well, right? So that concludes that particular problem. Right. Next problem. 4 students decide to perform an experiment on the velocity of sound. They are positioned as shown in the diagram below. So we have A, B, C and D, 4 students. They want to perform an experiment on this velocity of sound. They are positioned here. This is a building and there is this first floor on which D is positioned. Fourth student D is positioned there. A steady wind of velocity 30 meters per second blows from A to C. So wind velocity is from left to right, A, B, C. Across this direction, the wind speed is at about 30 meters per second. Here it is blowing. If B, which is at the ground floor of the building, he fires a revolver, what would be the speeds for the sound as measured by A, C and D? So now here B is firing a revolver, and what would be the speed for sound reaching A, C and D? That is the question. Right. First, let's calculate for A. For A, that is student A, the velocity is, let's call that the speed of sound, let us say, is US. US, right? US. There is a wind blowing, and plus the speed with which the bullet is fired. Right? So the sound of that would be, normally the speed of sound is in ambient conditions, it is 330 meters per second speed of sound. So sound velocity, let's call that is this. And therefore, we can say that in this case, the speed with which he receives sound is, because wind is blowing in this direction to the right from A to B, here A to C, and B is firing the bullet from the middle. So this is going to be minus 330, and that would be minus 300 meters per second for A. For C, who is on the right, from B sound is going to arrive at like this. So in this case, the same equation we can use US, the velocity of sound, and velocity of wind plus the velocity of the actual velocity of the sound. And that would be 30 plus 330 meters per second. And that would be 360 meters per second. So B is firing and C is receiving it at higher speed, whereas A is receiving it at a lower speed. The speed of sound is less. What about D, who is just on top? So for D, that is going to be the D is straight up and wind is going to this direction, so he is going to have a component in this particular direction. So we can draw, let's say, a triangle of this kind. Say that our US is now in this direction. This is the speed of the sound, and the actual speed of sound in still air is Vs, and the speed is this V. So if this is the case, since it's a right triangle, we can say that US is going to be square root of 30 squared plus 330 squared. The resultant answer would be US is 331 meters per second. So these are three velocities for the three students. Velocities of sound under the given condition. So that concludes our set of problems on classical relativity, Galilean transformation, and inertial frames of reference. Thanks for watching.